Why? Where's the table update? All right. So, Deephaven Live Table Monitor. We basically have a loop that is infinite for the life of your query that updates your tables. It starts off by, so stepping back a little bit, Deephaven tables form a DAG, a directed acyclic graph. There are some tables that are source tables that are roots of the DAG. So those tables must implement an interface called live table, which is basically a runnable, but it has one method named refresh. So the live table monitor will call refresh on all of the roots of the DAG. After that's done, that refresh, every table that has a listener will be notified. So there's a notification and there's a queue of these notifications. And there are dependencies. So if you look at the picture, for example, we have table A, B, and C. So those are refreshed at the start of the cycle. Then we have these derived tables A2 and A3. So when table A is refreshed, it will queue a notification to all of its listeners, and its listeners are often creating derived tables, but they could be doing anything else. They could just be printing out updates or doing any other kind of thing they wanted to with the table data, with the fact that it updated. Table B will queue an update for B2, and C would have C2 and C3. So after this initial source phase, what we do is we start processing updates from that queue. And we look at the updates and we say, is this update satisfied? Are its dependencies okay? Source tables automatically have satisfied dependencies. Other notifications are going to say, oh, is my parent satisfied? So A2 says, is table A satisfied? Yes. So then we can execute A2. We do similar logic for A3, B2, C2, and C3. So all of these notifications would be satisfied and eligible for execution. We have two modes of operation. One is we can do this single threaded. So there's this same thread that is asking the question, are these things satisfied? Is also going to be the thread that executes the notification. So in this case, we would execute A2. It has no downstream consumers, so we update it and it's done. Same thing with A3. B2, on the other hand, has a downstream consumer, this table BC. So B2 fires the notification, and when we want to evaluate whether this listener is satisfied, we'll say, oh, is B2 satisfied? And the answer is yes, because it's already executed within the cycle. But then you would ask the question, is C2 satisfied? And the answer is no, because it has not yet executed for this cycle, but has the possibility of executing. So we can't run table BC's notification until after C2 is done. So next we can execute C2. That's completed, at which point this notification would be satisfied and is eligible for execution, the one for BC. Actually, you can't see my, I don't know if you can see my pointer. Probably not.
Yeah, we can't.
Yeah, so I was pointing at BC saying, hey, now it could execute even though it couldn't before. So if we're single threaded, we're just going to proceed in the order that these things become satisfied. So we'll execute the notification for C3, and then finally the table for BC. Now, this gets a little bit complicated when we're doing multi-threaded stuff. So if we're multi-threading, we have some number of update executor threads, and then we have the main refresh thread. So what happens is the main thread executes to a first order approximation, no notifications. All it does is it submits things to a queue, which then an executor service will pull off from. And it will only put the satisfied notifications on that queue when so then what would happen is, let's say we had two threads. We would start A2 and A3. And let's say A2 is taking a long time, but A3 finishes. We would then say, well, what's my next satisfied notification, which would be table B2. So we could start executing that immediately. Let's pretend A2 finishes, so we have another slot. We'll execute C2, and let's say that's really quick, so it finishes. That's going to cause us to evaluate the pending notifications and determine BC is not yet ready, so then we'll execute C3. And when we finish C3, let's say that happens quick, that's done. Now we have one thread that's executing B2 because that didn't finish yet. And the other thread is idle because there's no work left for it to do. That's satisfied. When B2 completes, then both C2 and B2 are done. The refresh thread will look at the outstanding notifications, which are only BC right now, determine that that's satisfied, and put it on the queue for the executor service. So then we'll execute BC because it's been satisfied. And at that point, we've executed all of the notifications, we're done, and we'll start this whole process over. So
okay, so let's pause for a second for questions, just because there was a lot of complicated stuff here.
So this will sound horrible, but I just want to be perfectly sure I'm crisp about what update means. Mm-hmm. So I think you're asking like one of these components to update, and what you're really saying is like, well, hey man, here's your chance to generate some rows, and they might generate 0 rows if no data from their source, whatever they're doing, has arrived, or they might generate all the rows because it's the first time they've ever been updated, or they might generate like some incremental batch of rows that says, hey.
Oh. You are 2/3 right. So,
oh man,
hey, that would be passing, 56%. On the refresh, these source tables, they could generate no rows because nothing happened. They could also generate some number of, usually source tables, if they're a disk-based table, are going to be append only, so we'll add new rows. But they can also take away rows, modify rows, or shift rows. So, for example, the Kafka model is we're creating this stream table that will add rows and then remove them on the very next cycle. You can have a timetable that just adds rows, every second or whatever interval you want. What you mentioned is, it's the very first time I updated, so I'm going to add all the rows. That's not how that works. The initial time, there's an initialization phase for all of the table operations that takes place not on the live table monitor, but on whatever thread is doing the operation. And that will look at the table as it exists. And there's a little bit of complexity around that. If you're trying to initialize things concurrently with the update processing. So all of these update processing notifications have the ability to look at both the current values and the previous values for a table on the graph. The the current is the newly updated value. The previous is what it was at the start of the cycle, not what it happened to be the last time it updated. So, and then when we get past a source table, it also gets, arbitrarily complex. So for example, if you had a where clause and you had some rows added, you might produce no updates because there's no rows that pass through your filter that your filter would accept, or you might produce a subset of the updates from the source table.
Okay.
You can also have more complicated where filters that are somewhat like a join. So there's a where in operation, and if the set of things that you ask for, let's say you're doing a where not in, you might have a row added to the exclusion set, and that would result in rows being removed from a downstream table of the where. So those nodes that are the derived tables can pretty much do arbitrary things. The one rule is you're only allowed to notify once per cycle.
So that means it's a push. That means a table is saying, "Hey, I have rows."
Yeah.
Okay. Not being pulled. Not being pulled or pulled.
Yeah. So there are a few cases where there's a pull. The one thing is if you're doing a snapshot, then you get a push from the trigger table, like the timetable, but you would pull from the right-hand side table that you're trying to snapshot.
Okay.
And that pull still needs to respect dependencies, even though there's no listener on the right table.
Okay. I think I understand that.
Okay, so Charles, in the event that there is no change, is there a no change update sent down the line or nothing?
Nothing.
Okay.
So
you kept saying satisfied. What exactly does that mean? That a table is satisfied?
It's really that a notification is satisfied. It means that either every dependency that the notification has ticked on this cycle, has sent its notification, or it will not send its notification. That there is nothing to notify on. So if you have a source table, right, there's this initial phase of all the source tables updating, refreshing. So if they were going to refresh, they have to do it at the start of the cycle if they were going to send a notification. So that means that a source table is always satisfied. Then, like table A2, there's going to be a listener, and its listener will be satisfied if table A is satisfied and that listener has executed its notification. So if there's no notification for the listener, if nothing has been enqueued, then, okay, we're after the initial state, so nothing can get enqueued. But if we have an enqueued notification, we need to wait for it to be done, and then descendants of table A2 could actually do something. But they can't proceed until they know table A2 has already updated or it can't possibly update.
Yeah, so the short answer is you know that all of your parents, you have the update events from them.
Yeah.
So they're done.
They're done.
For this cycle.
So you now have all the data you need to compute.
Okay. Yeah, that makes sense. Okay. Yeah.
So, I mean, I guess I have sort of the same question, because what about synchronization? Like if some source is time-based, then it might produce a batch of rows that are the wrong epic
it has
window,
to
right?
capture a timestamp at the refresh, and then that is what it is based on. So
Okay.
there's at this refresh, you have a distinct point where things have happened or they have not happened, right? So if
Okay.
it's a timetable, we'll advance it to
Great.
whatever the current time is. That might mean you had 3 rows. That might mean you had no rows. But whatever it is, it happens at the refresh, and you get 1 notification per cycle.
Well, okay. So I'm not sure I understand. So I don't know. Like, let's imagine we have 2 tables and they're going to feed a join, right?
Yep.
And one table has a really fast source, like it just gets rows. And
Yep.
the other table, like it takes a long time. Like it's on some slow link, or it has to retry or whatever, or someone wrote it in a really slow language like Java, and it just takes forever to go get rows, right? And in it, so like look, I get rows for 10 seconds from the fast guy, and then I go update the second guy, right? The right side source or whatever. The join still isn't satisfied because it needs rows from both sides. The right-hand side is waiting and waiting and waiting.
We're refreshing those, whether they're concurrent or not,
Yeah.
A, B, and C
Yeah.
at the beginning of the cycle. So
Sure.
we wait for all of those to complete refresh. So that it's however many rows they're going to give you, right? They
Okay.
can take however long they're going to refresh, and they release those rows. So if table A is really fast, it's going to give you the rows that it processed at the beginning of the cycle, whatever was batched up.
Sure.
And table B will do the same thing. Maybe it's slower, so you don't get as many rows, but you get whatever was available.
Sure. But that would
And
mean on the next on the next refresh, right? Wouldn't it be that table B ends up producing rows that don't necessarily match the time frame of the rows that most recently came from table A?
So there's no guarantee about that unless you were to create a combined live table that has 2 source tables basically that would somehow synchronize each other, but that's not how it's normally going to work. That whatever data you receive is the data you're going to present, and you're not trying to synchronize your source tables.
Well, but for completeness, you have to eventually, right? Like if A is outrunning B, then there's some lag, and you still want to join everything, right? Which means there must be some queue or some,
Well, it depends on how that works, right? If B is just behind because its source is slow and can't keep up with the update rate, it's going to fall further and further behind. We'll update your join with, whatever join to whatever as they exist at the start of that cycle. And if it's really that one source is slow, like, in enterprise, how that would happen is, one source is unable to write its logs quickly enough, or we're not able to ingest the source for that logs quickly enough. You could have one table that's at 2 o'clock and one table that's at, 10:30 because it's terrible. And then at 4:15, when everything shuts down, things start catching up. And, that's an extreme case where, you have to figure out why your system isn't managing. But you can certainly have things on a smaller scale where one table isn't up to date with the other table, but eventually, you get a consistent view of some point in time for A and some point in time for B.
Okay.
You can, at the application level, if you have, for example, transaction IDs or other things, if you're writing multiple tables, have them kind of go in lockstep, which we've done for one of the enterprise customers.
Yeah, when I was in the trading world, I always had a query running that would look at the latest timestamps for my critical tables, and if that tolerance exceeded something, then I would shut down the trading. And so, you can use the system to monitor the latency as well. But, like Charles said, you can just process what's there.
Okay, thanks. I think I get it.
Okay. So while all this is going on, the live table monitor takes an exclusive lock. And it does that on the primary refresh thread.
But Charles, before getting into that, can you explain the scope of the lock?
So the lock protects all table updates. So you can only read data if you hold the lock, and you can hold it shared or exclusive. If you're updating the DAG, which only the live table monitor should be doing, then you take an exclusive lock. Pretty much in every other case, you can take a shared lock. If you just try and read data without doing any kind of synchronization, bad things are going to happen to you, right? You don't know whether you got it all on the same cycle, on multiple cycles. It'll just be unpleasant. So there is basically the equivalent of a giant or BKL that
Ask what it is if you don't know.
is inside of your worker. Because
What is it?
What
What is a BKL?
Big kernel lock. Giant is the FreeBSD kernel's big lock. So a GIL in Python, just global to the process.
Okay. Cool.
So you have, each worker will have its own lock because they're independent processes with independent LTMs. There's no synchronization of these things across the network, across anything, right? So if you had one thing and then you had another thing with a barrage source table, you're not linking their update cycles together. The client in that case would coalesce barrage updates and notify for all of the received updates at once. Which goes a little bit to Mike's question about synchronization, and that the coalescing does help with that, because as you get slower, usually it's the case that handling fewer, bigger updates will cause you to process them with higher throughput, as opposed to lots of little updates. Not that you have terrible cycles no matter what, but so you have this big lock, and we take an exclusive lock before we start updating tables, and we only release it after we're done updating tables. So there is also, and then in between these LTM cycles, we basically have a target time. So by default, it's 1 second. We've gone down for production use cases as low as 50 millis when we're trying to interdict trading. I wouldn't go too much lower than tens of millis. It's not going to be helpful, but you have this intercycle sleep, basically. So let's say we didn't take the full 250 millis. We're just going to go to sleep waiting for more data. Things might be trying to read data, and they can instead take a shared lock. So if you take a shared lock, any number of readers can get data at once. And they will block the LTM thread from processing new updates. So for example, if you have a UI that's trying to do a filter, that might require a shared lock, at which point your LTM thread won't start processing its cycle, because some other thread has the shared lock, which blocks the exclusive lock. There was a gotcha that I wanted to mention about multi-threaded LTMs, which is that the refresh thread takes the exclusive lock. The update executors don't take a lock, but they know they're on the refresh thread and kind of protected by that. The update executor is protected by the refresh thread holding the lock and the dependency management, which ensures that you're only going to look at tables that have already been updated. So there's some finesse there in that if you have listeners which would try and do new table operations or take a lock, you're going to end up deadlocking. So there's a method on the LTM that allows you to ask, hey, am I a refresh thread or not? And then do different things depending. So it's also important to realize that in addition to the LTM being this global thing per worker, there's what we call a logical clock. So if I go to developers, Java docs, so there's this logical clock class. So there's two states for the logical. I thought I changed it. Okay, hold on. I tried to switch my tab. So no, it's still not updating. Oh, Java doc is opening in a new tab. That's why. So there's this logical clock. So the logical clock has two states. It's either updating, so that at the beginning of an LTM cycle, we say the clock is updating and we increase its step. And then at the end of the cycle, we say that it's idle and we leave the step alone, so that you'll go from step 3, idle, to step 4, updating, to step 4, idle, to step 5, updating, to step 5, idle, and just so on and so forth, basically forever. And what that clock allows us to do is understand if something has been updated on this cycle or not. And that is important for tracking previous values, so that we know what the old value is for something like a sum. We don't actually recalculate everything, which, the prod support people were, some of them at least, confused about, because they were adding up a bunch of numbers and then subtracting the numbers in some other arbitrary order. And like, why isn't it 0 when, it's epsilon away from 0, because it's math, right, on a computer using floating point. So the point there is we're not recalculating everything from scratch. We're only recalculating the deltas. And to recalculate those deltas, if we had a value change from 5 to 6, we need to be able to subtract 5 from the sum and add 6 back in. And the logical clock is an important part of the internal data structures for understanding how that thing works.
So since we're on clocks, can you mention replay?
So this is, Replay is going to generally be bound to timestamps. So this is a logical clock. So like it has nothing to do with wall clock time. You know, it's basically a counter of how many LTM cycles have executed within a worker. Replay is going to be basically a source table that we have a filter on, and that filter will itself be a live table, so that as real time advances, more rows are released from the filter. So that way the downstream consumers see them. And there's a replay database that will automatically apply clock filter to do that. But that is totally independent of the logical clock, which is well, we don't have clock filter in the Java for replay database. And you know, there's no reason for you guys to filter Java doc, and we're going to just stop doing it in enterprise on the next release. But
Yeah, we're not filtering now.
yeah, we have to wait for Bard. But the replay database and clocks are different. So it would be, you know, it's, I think,
Okay. Before going back to questions, can you cover AMDR messages?
yeah, so there's listeners. They have a shift-aware listener update. So there is an older version of this that just has added, modified, and removed. We prefer not to use that because the new listeners support two things. They support shifts, which just tells you to understand this message, you really need to understand what makes up a table. A table is made up of columns and an index. Columns are, or column sources in particular, provides a get method. There should be get in here. Why is get not in there? All right. The guy to fix my garage door is here, and it's been broken for a month. So this is our stopping point. There's two things we need to cover. We need to cover what makes up a table, which then lets you talk about an update. And then we also want to talk about how to lock to read, which I have a Jetty REST example for. So I'm going to, those are kind of probably the next two topics. You know, what to do with a listener in an update after you know what makes up a table, and then how to read from tables in fancier ways than taking the shared block.
Okay, so we don't block you on your garage door opener. Let's talk and try to figure out when you can cover those two.
Okay. All right. Bye, guys.
Bye.
Thanks, Charles.
Bye.
All right. Any questions on that? I realized there was a lot of stuff there.
It's pretty thick. I guess one thing I'm not positive I understood was the purpose of replay. Like, when would a replay happen? Why would a replay happen?
Okay, so let's say you have some old data.
I have some old data.
Right, and you want to see what it would look like as if it were real time, right?
Oh, okay. All right.
Does that make sense? So,
Yeah,
for
okay,
example, you could simulate trading, or maybe you had a bug, so you wanted to try to recreate the same scenario or whatever.
Got it. Yeah. So you're trying to refresh data that's not the current right now timestamp.
Yes.
Okay, great. Okay, got it.
Yeah,
Okay.
yeah, and in POCs, we've frequently had cases where prospects don't have a real-time data source, but they have historical, and they want to see what it would look like if they had a real-time source.
Yeah. All right. Got it. Thanks. Yeah, I thought it was something much more nefarious than that.
Yeah, not so much.
So if you have a root table that's updating, and then you have a bunch of downstream tables that are like doing calculations on those rows,
Right.
giving you new ones. So what happens is that the first one, the root table.
You're talking about in the LTM?
Yes.
Okay.
So the root table updates.
Yeah.
And they say we've updated, so we're going to have a lock because we want to stay consistent with all our downstream tables.
Not exactly. So you have a clock cycle where this thing updates,
Right.
and at the start of the clock cycle, it grabs a lock.
Regardless of whether the table has updated.
It doesn't matter.
Got it.
Then it says, okay, for these source tables,
Uh-huh.
process that down and propagate it down.
Yeah.
And then keep propagating and compute everything you can compute
Uh-huh.
until you're out of things to compute, then release the lock.
And then, okay, so what happens if those computations take longer than the table cycle?
Okay, then your cycle time will end up being longer.
Oh,
Okay.
okay, so it won't just,
It won't lock up, but it will be longer.
sure. That makes sense.
And so if you look at the performance stats, what you can look at is how long the cycle times were.
Uh-huh.
And if you start seeing long cycle times, those are places to start looking for performance problems.
I see.
Right.
I see. So could you like potentially avoid that kind of thing by just setting the cycle time to be longer by default and processing more updates at once? Or
Maybe it depends on the nature of the problem.
sure. Yeah. Okay.
Was there too much data? Was the calculation too long? Was whatever.
Okay. Makes sense.
So that's essentially the same question I'm trying to ask about at the source, right? Because like the source is slowing things down, right? And it seems a little harder to make sure things are synced.
Okay, so the source won't be slowing things down. The source can say, I have data, right? And then, the internal clock cycle will continue no matter what. Whether that data is timely or not from the source is a different question.
Yeah.
Right? Does that make sense?
Yeah. And but that's what I mean. When it's not timely and there's a subsequent blocking query, a blocking operator that needs input from both and needs the input to line up.
Okay,
right?
so you're looking at this like a pull rather than a push, right? So the data sources,
probably am. Yeah.
The data sources, what they're doing is they say, here's my data change, here's my data change, here's my data change. So nobody is waiting. It's just computing on the latest change.
It doesn't care if it's timely or not, the resulting tables.
No, it's it's the responsibility of that data feed to make sure itself is timely.
Right.
Does that answer your question, Mike?
Maybe. Say we're joining two sources. The left-hand source is like, hey, I have data from 1 o'clock and I have data from 1:01, I have data from 1:02, right?
Mm-hmm.
And we want to join those. And so far, the right-hand source hasn't said anything. And then finally, it says, hey, I got data from 1 o'clock. I mean, in real life, it's probably like 1:04 already. So what's going on? Like, what happens? Like, I guess the join sees all the data from the left-hand side from 1 o'clock all the way through 104, and
Yeah.
only sees the right-hand data from 1 o'clock because that's all it's got so far. Yeah.
Okay, but remember, it's not just looking at the delta. It also has the history if you're doing a join.
Great.
Right.
Great.
So-
Perfect. So where is that? Who manages that? Where's the history stored? What's going on? Why? What?
So that's in the table implementation. It's dealing with that. So you can imagine another case where we want something that's not a table. Let's say we wanted an object that's like a singular value decomposition or something. Well,
Okay.
then if we implemented that, then we'd have to deal with all the state stuff, which would make it a big project.
Yeah. Okay. I think I got it now. I think I'm there. I think I understand how it fits.
Right. What else isn't clear? We did a lot of stuff. So, we did the update model. We did locking. We discussed replay. We started discussing AMDRs.
I guess one bit. I hope I'm not monopolizing things, but one thing that wasn't clear about locking is, well, who's locking, right? Like there's this large scale lock. What contention exists for the lock? Like, I think Charles said, well, we lock, the whole update happens, and then we unlock. So who would be trying to do something during the lock? Well, like who else is pursuing that lock? What's the scope of the lock? What?
Yeah. So okay. So let me give you a more complicated example. So
in saying like, look, we'll wait for Charles next time or something. That's fine too. I mean, I don't.
Yeah. I guess let me give you a more complicated example. So for most use cases, the LTM has a do locked function where you can tell it to execute this within the lock, and that's pretty straightforward. If you're within like an update call, the lock is already, if you're within a listener call, that lock is already held, so you don't have to think about it. That just is happening in the background. So a case where you have to think about holding the lock. So in one of the things we implemented for a client was basically a thread pool for performing options calculations. So these calculations take a long time and are pretty computationally intensive. So, we couldn't possibly compute this every time a table ticks. And so what this does is it basically creates a pool of threads. Every time one gets freed up, it says, give me the next thing to compute.
Okay.
Then when it does that, then that object holds the index of where the data is stored. So at that point, it needs to grab a lock to go read the stuff from that index. So it's not updating while it's trying to read it.
Yeah. Okay.
Yeah, so 99.9% of users will never care about a lock.
Yeah.
It's just when you're trying to implement something more complicated where you're getting a column source and trying to read values, you need to make sure you're not reading them without a lock.
Got it. Because they could be updating, and the lock just says there's an update.
Yeah, right. And even within that, almost all the time you want to get a shared lock.
Yes. Okay. Great. That helps. Huh. Interesting. Huh.
And in everything that I'm doing, that's just baked in because
you're doing it through an update.
Yes.
Right.
Yeah.
Right. When you looked at the stuff earlier on, you were having to think about how to do that other stuff.
Right.
It was getting complicated.
Right. But the update, it just knows how to do that.
Right. JJ, Amanda, any questions?
Is the lock and unlock feature available in the community edition yet?
Yeah, it's there. It's even available within Python. There's it's like a do locked or something like that. Just search the Python docs for lock, and I think you'll find some examples,
Sweet.
or at least some docs. All right. Yeah, and if you look at the Python listener example, it'll show how to create a listener, and it'll show these update messages coming in, and you could look at them and just see what that looks like. I think the example just prints out some values, so it's an easy way to play with it to get a feeling for this stuff.